Assalamu alaikum everyone, this is Atiya Ahmad from IBA. In this video, we will be reviewing my project for Big Data Analytics taught by Mr. Shabir Makri. A brief overview of the project is that it involves both data analysis and the infrastructure required to perform that data analysis on a humongous data set. I must admit that the focus on data analysis is quite light compared to what is the focus on the infrastructure from my end. So to begin, first let's talk about the dataset. It is an official TLC trip record dataset that contains more than 1.5 billion taxi trips from January 2009 through June 2019. The size of this dataset was 50 GB in 2018 and is probably much more by now. And the dataset contains a total of 20 variables such as location coordinates, fare amount, payment method, distance travel, so on and so forth, all of which are not mentioned here due to a lack of space. In order to be able to perform data analysis on this dataset, we require a big infrastructure which comes in the form of Azure HD Insight, which is a cloud distribution service of Hadoop components. It enables us to create optimized clusters for Hadoop, Spark, Kafka, Storm, Edgebase, so on and so forth on the cloud, saves us massive amount of time, is easy, cost effective, etc. So using these various components provided by the HD Insight, we have basic infrastructure set up for a data analysis service. First, we have the data source. The data can be either on premises or cloud. Then we have another service called Azure Data Factory provided by Azure in itself. It allows us to ingest data from various sources to a certain destination. That destination must be some form of cloud storage provided by Azure. Source can be anything. Once the data is stored within the cloud storage provided by Azure, then the clusters provided by HD Insight can be used to read data from the storage system and perform processing on them as required. We can also visualize them through either Pythonic layers that are built on above clusters such as Spark, or apply machine learning services on them. And we will be using a Spark, which is a parallel processing machine framework that supports in-memory processing to boost the performance of big data analytic applications compared to conventional Hadoop, which reads data from the hard disk each and every time. Apache Spark in Azure Edge Insight is basically the Microsoft implementation of Apache Spark in the cloud. It just makes it easier for us to create and configure a Spark cluster in Azure. So Spark clusters in HD Insight are compatible with Azure Blob Storage, Azure Data Lake Storage Gen 1, or Azure Data Lake Storage Gen 2. This is the basic architecture of a Spark cluster. We have, as usual, the head node, which has the cluster manager or the yarn cluster manager in it, as well as the Spark context object, which is essentially our driver program called the main program. Then we have a worker node which have executors in them, which basically execute different tasks that have been given to them by the head node. Finally, we have the HDFS where the data is stored and read from. We have the data store. So Azure provides data stores that are specifically compatible with HDFS and Hadoop environment. So these data stores are designed for analytical systems that require massive throughput to query and analyze large amounts of data. The data lake spreads parts of a file over several individual storage servers. So it's essentially a distributed system. So let's go over the demonstration. First, let's demonstrate a data storage that we have, which is the Data Lake Gen 1, which as we know is compatible with HDFS. It is virtually unlimited storage, so we can store all of our 50 GB of data in there. Right. So let's go to our storage accounts. We have our storage account, Hadoop storage 123, and within this storage account we have a data storage that is called as the Hadoop cluster container, which I'll show you just right now. If you open this and go to the Hadoop cluster container, this is where all of our HDFS associated files are located that you can see. So this is a HDFS compatible container. Additionally, we have a data set right here. It's called NYC taxi fare. If you double click on this, then you can see our data set is divided by years. So for instance, if I go into 2013, we have data set further divided by months, and if I go into the third month, Then this is my data that has been distributed into various Parquet files. Parquet files because they are essentially space efficient and is fast as well. So these Spark clusters will read the different Parquet files and then will transfer all of the data that they have read into their memory. Right, so this is our Hadoop storage. We want to upload the data. We can simply click on here, click on browse, and then select our associated files and upload the data as necessary. However, while this method of uploading may seem feasible for small files, it is certainly not for datasets that are as large as or greater than 50 GB. Instead, for them, what we have to use what is called a Azure Data Factory. So an Azure Data Factory is another service provided by Azure which essentially allows the creation of workflows for orchestrating data movement at a scale. So using that, we can create pipelines that ingest data from disparate data stores or Azure's own storage and then transfer it to ours. Right, so we have two examples. We have on the left side where we are configuring the pipeline. We are setting the source and the destination, where we are specifying the source as the Azure the storage system where all of the open data sets are stored, and the destination as our own storage system, which is Hadoop cluster container where the data needs to be stored. Finally, we have on the right hand side an executed pipeline. So you can see the source of the pipeline is Azure's, the destination is my own storage system, and then the pipeline was successful, which basically means that it copied the data successfully from Azure's storage system to my storage system. As an example of this, we'll just go through with it. So this is a data factory. This is where you configure all of your pipeline. We specify the source, we then specify the destination, whatever varies the settings are, and then we execute the pipeline, which as a result essentially transfers all of the data from Azure's storage system to my storage system. This is how the pipeline works. Let me show you a pipeline that we already have. Let's see if I can open that. Right, so you can see copy pipeline underscore 0IGB. This is a pipeline that we made a few weeks back. If you look down, we have the source. We specified the source as Azure's data storage system, and then further that, if I open this, I specified that within Azure's storage account we have the container nyc tlc, and then within this subdirectory called yellow is where our data lies. Finally, I said that I want this data to be transferred to my storage container or my storage account. My storage container names is Hadoop cluster container, and I want this data to be transferred or copied to this subdirectory, right? So once I execute this pipeline, which is basically by clicking on publish all, it will execute this pipeline and transfer the required data into my storage space. Now once that data storage has been set up and data has been transferred, we need to set up our clusters. Now to set up our clusters, this is my cluster, right? So usually what you do is you create on click cluster. I'll just click on it right now for making sure. Yeah, so you click on clusters, you make the specific set the specific configurations, you name your cluster, for instance 123.0.8. You select the cluster type that you want. So for instance, I want to work with Spark. I select a Spark, right? So you go to storage, you said okay, I already have a storage account, I don't need a new storage account. I want my clusters to be associated with the specific storage account to which I have already transferred my data to. Finally, I go to the configuration setting and then I select the configurations of the node that I want to work with. So how much memory do I want a worker node to have, and then each node has its own pricing system. So this is how clusters are created. I already have a cluster created. So for instance, if you go to the cluster side, this is the configuration of my cluster. I have 2 head nodes which have 28 GB RAM and 4 cores, Zookeeper node, and then 6 worker nodes which have each 28 GB RAM, right? So this is my cluster side. Now these are some of the most important things. So first off, how do I monitor my Hadoop dashboard, right? So first we have this dashboard of Hadoop that is completely there for us. So for instance, I can if I go to the dashboard, I can have all the details. This is my name node here, this is my disk usage right now, CPU usage. I have this is my node has been my name node primary node has been up for 3 days up till now, up 3 days 12 hours. I have all 6 data nodes that are live right now. Anything that I specifically want to see about HDFS, I can see it from here. I can see the data nodes, so on and so forth. If I want to see about yarn, I can go into this. I can go into basically different heat maps, configuration, metrics. So this is a whole dashboard that's been set up for us to be able to monitor our cluster in a whole, right? So this is how we monitor our cluster. Then we have what's called a Spark history server. So in a Spark history server, we are, for instance, if we open an application, we are able to see the jobs that we run. So for instance, I called several pandas functions, so we can see a job was run for each function that I called. It ran for this duration, and then whether it succeeded or not, so on and so forth, right? So you can keep a track, or you can see the track, the logging that is essentially going on. You can also see the yarn cluster manager. So this is the whole yarn cluster manager. For instance, an application was running, it started at this time, ended at this, was successful. In some applications I had to kill them because they were running for too long, and my Jupyter notebook had essentially collapsed because of the load that was required. So this is how you manage or review your whole yarn manager. Finally, we have the Jupyter notebook where we write all of our codes. Now I'll open it from here. I won't press enter because this takes time to load. So this is where our Spark session is started. This is where I specify what container I want to access, whether I want to access my own HDFS compatible container or Azure's own storage system, right? So I specify the container details, then I basically read the Parquet files that we saw. We read all of the data from the storage system, and then we create a virtual table and load it into the memory. Once the table has been loaded into the memory, we go on to perform pre-processing of data. So we create user-defined functions. User-defined functions allow us to perform specific functions or call specific functions on the values of columns and create new values. That new values can then be assigned to either existing columns or new columns. So this is what user-defined functions allow us to do. This is what happens in whole user-defined functions. Now the thing is, this may seem somewhat contradictory. If you know, we have been working with a dataset that is as large, that contains 1.5 billion records. Now, when we try to load all of these 1.5 billion records through the virtual table, we are successful. But the thing is, in order to be able to plot these data points, in order to be able to perform a bit more complex operations on them, right, perhaps parse them or filter them, then we need to convert all of the query or results of the query being returned to us to a pandas data frame. But pandas data frame cannot really handle large data sets. It can only handle small data sets. So we need to sample data set from what we currently have. We can't really work with 1.5 billion data sets. So what I decided to do was only filter out data points from the year 2013. 2013 is known as the data that is most accurate for the NYC tax return data set. So we filtered out 2013 data set, and we dropped from 1.5 billion to 173 million. A big drop, but unfortunately at 173 million it was still crashing a lot of times. It could not handle because it could not convert the results to a 2 pandas data frame, nor could it parse the data frames essentially, right? So we had to further sample it by month. So what we basically did was, in the year of 2013, for each month we sampled 0.01% of the data, which would amount to almost 150,000 data points for each month within the year 2013. And so at the end we had 1 million 1.7 million data points ready for us to analyze. So we decided to analyze. We've performed some further pre-processing on the data. For instance, in one of the tasks, we decided to study consumer behavior and when does a customer decide to tip. So we had to convert our tipping values to binary values, right? So if a customer did tip, then it was 1. If they didn't, then it was 0. Then we had to discretize some continuous values or continuous columns. Similarly, we had to so we had to encode some discretized columns, and then we had to cluster some columns as well. So for instance, if you see, we have a start longitude and a start latitude. These are the pickup points, and similarly we would have end latitude and end longitude and end latitude, which would be the drop off points. So what we did was we clustered all of these into 3 different clusters. So essentially we had 3 different points from which taxi drivers were picking their customers, allowing us to study behavior of each point in its own right. So this was all of the pre-processing that we did. So for instance, we once again discretized some things. We ran a cluster here on longitude and latitude variables. We removed some outliers that were there and some values that were null. And then we finally started working on our data analysis. So for the data analysis, I'll open my PowerPoint. So yes, as I said, we did data sampling. We had upon 1.5 billion records, but we couldn't deal with all of the new technical difficulties. So we had to sample data for each month of 2013, and in the end we had 1 million records, around that number representing each month of the year. Then we did some pre-processing of the data. We introduced an additional column in which we assigned a value 1 if tip amount was 1, greater than 0 and 0 otherwise. We discretized TPEP pickup date time and TPEP drop-off time. For instance, if the pickup time was between 6 a.m. 12 a.m., we said that the driver is picking the person in morning, and then if between 12 and 4, then in the afternoon, so on and so forth. We also clustered longitude and latitude variables for us to be able to work with drop-off and pickup points effectively. We through the pickup and drop-off date times, we introduced day and date. Basically, for instance, if the driver picks someone from the 10th of October, then basically they picked someone on Wednesday. So how does a certain variable vary against differing Wednesdays? To investigate that, we introduced a new string day variable, which is basically weekend or weekday, Monday to Sunday. And then date is the 10th of October. So 10th is basically the date in itself. We removed some outliers. So then finally coming on to the behavior, we decided to first determine whether we managed to find some tipping behavior. So when do customers really tip? So first of all, we plotted a distribution of the passenger counts. We saw that at least almost all of the people, or major chunk of the people that travel in taxi are alone. And then we decided to compare the distributions of who tips and who doesn't tip, and we saw that there really wasn't a significant difference between the two, so we didn't really spot a large correlation. Then we decided to study tipping behavior against tip distance, which basically means that if the distance traveled in a taxi is long, then is the customer more likely to tip or not? So people like travel very less distances. Long distances are rarely traveled, as we can see in both of the plots. And then again, there's not really a significant difference between people who tip and people who not tip. So the likelihood of a person tipping is actually the same. We also decided to see tipping behavior against customers who perhaps travel in the afternoon, morning, midnight, so on and so forth. Didn't really spot a big difference. As you can once again see, distribution is more or less the same. Then we decided to study trip duration. So we know that once again, since distances are being traveled small, trip durations are also very small, and then very long durations are very rare. We again decided to study trip duration against passenger count. Didn't really find much. Trip durations were more or less the same for every number of passengers. we decided to study trip duration against specific days. Didn't really find again a significant difference. Then we decided to study it against pickup times. Once again, we found that trip duration during midnight seems to be comparatively less, probably due to less traffic, but nothing very major. However, we decided to do the same plot for all of the 5 days, which we noticed that at least on weekdays, the trip duration during midnight is almost always less when compared to other time of the days, which is probably because the traffic during midnight is also less. Yes, as discussed previously. Finally, last but not the least, we did decide to do pickup density analysis. If you remember correctly, we clustered longitude and latitude pickup and drop off points into 3 different clusters. Almost all of the people were picked from the cluster 0. So you can see that there's a major imbalance within the data points, so we really couldn't analyze a lot. This was for the project. If you have any queries and concern, please reach out to me. Thank you.